You ever see a news report that says something like, "Scientists know the average weight of every blue whale on Earth," or a political poll that predicts a whole election just by calling 1,000 people? I mean, how do they do that? It feels like magic, right? Well, it's not. It's this incredible tool called statistical estimation. So let's dive in and see how we can make these super smart guesses using just a tiny, tiny piece of the puzzle.
All right, to really wrap our heads around this, let's kick things off with a question. A question that, at first glance, seems absolutely impossible to answer.
Okay, so picture this. A huge university, maybe 30, 40,000 students. And your job is to find the average height of every single one of them. I mean, seriously, how would you even start? Are you going to run around with a tape measure trying to hunt down every last student? No way. It would take forever, cost a fortune, and hey, by the time you were done, a whole new class would have started and others would have left. It's just not practical.
And this is where the magic of statistics really shines. It hands us this amazing toolkit for tackling exactly these kinds of impossible problems. See, the secret is you don't need to measure everyone. You just need a really clever way to take a small piece of the puzzle and use it to see the whole picture.
So how does this actually work? Well, to get it, we need to talk about a really key shift in thinking. It's what makes statistics different from its cousin, probability.
This slide nails the difference perfectly. Think about probability. That's like you know all the rules of a card game, you know exactly what's in the deck, and you're trying to predict the odds of getting a certain hand. You're going from the big picture, the whole deck, down to a specific thing, general to specific, right? Statistics flips that completely on its head. It's like you're just handed a few cards, and from that hand alone, you have to figure out the rules of the entire game. You start with the specific, your data, and you work your way up to the general, the whole population.
And that whole process, that act of working backwards from the data you have, it's got a name, and it's called statistical inference. The best way to think about it is like you're a detective at a crime scene. You didn't see what happened, right? But you've got clues, fingerprints, a footprint, whatever. You take those specific clues, your sample, and you infer what happened. That's our main tool here. Okay, so if we're playing detective, we know we can't talk to everyone in the whole city. It's just not possible. So we have to pick our witnesses, our sample, and we have to pick them really, really carefully, because honestly, the success of the entire case hinges on this.
So let's get our terms straight. First step, the population. That's the entire group we want to know something about. In our university example, the population is every single one of those 30,000 students. That's the whole shebang.
And then we have the sample. The sample is just a small, manageable chunk of that population that we actually look at. So instead of trying to measure all 30,000 students, maybe we just measure 100 of them. These 100 students are our key witnesses. They're the ones giving us the clues.
And this is so important. It's all about how we pick that sample. It can't just go out and measure the first 100 people you bump into. I mean, what if you accidentally ended up measuring just the basketball team? Your average height would be way off, right? Or what if you only measured first-year students? Your whole conclusion would be totally skewed. Everything, and I mean everything, depends on how you choose those 100 people.
The absolute gold standard for this, the best way to do it, is called random sampling. It's pretty simple in concept. You just have to make sure that every single student in the entire university has an equal chance of being picked for your sample. When you do that, you avoid bias. You end up with a small group that's basically a miniature, representative version of the whole population. And that gives you clues you can actually trust. All right, we've done the hard work. We've chosen our witnesses carefully through random sampling. We've gathered our clues. Now it's time for the big moment. It's time to make our single best guess about the whole population. To make that guess, we need a tool. And in statistics, that tool is called, well, a statistic. I know, it sounds a little weird, but it's really just a fancy name for any formula you use on your sample data. The one we all know and love is the average, or what statisticians call the sample mean. You know how to do it. You just add up the heights of our 100 students and divide by 100. Simple as that. Now, when we use a statistic, like that sample mean we just calculated, for the specific job of guessing the value for the entire population, we give it another name, a point estimator. Think of it this way. It takes all the messy data from our sample and boils it all down to one single number. That one number is our best guess. It's our detective pointing a finger and saying, that's the answer. Okay, let's walk through that one more time, step by step. Step 1, the goal. Find the true average height of all 30,000 students. Step 2, the action. We randomly pick and measure just 100 of them. Step 3, the tool.
We use our formula, the sample mean, on those 100 heights, and boom, step 4, the result. We get a single number. Let's say it's 5'8". That single number, that is our point estimate, our single best guess for the entire university.
So, we've got our number, 5'8". Great. But how good is that guess? Should we bet the farm on it? Is it a fantastic guess or a terrible one? How do we even judge the quality of our detective work here?
Because, you see, the sample mean isn't the only tool in our toolbox. There are other formulas, other estimators that we could have used. So if you've got a couple of different ways to make a guess, how do you know which one's the best, which one's the most reliable?
Well, it turns out statisticians have basically created a report card for estimators. They look for a few specific qualities to see how good a guesser is. We're going to look at 3 of the big ones: unbiasedness, consistency, and efficiency. So let's quickly break down what each of those means.
First up, unbiasedness. This is all about being fair, not having a favorite direction. So imagine an archer. A biased archer is one who always consistently shoots a little bit to the left of the target. But an unbiased archer, their shots might be all over the place, some high, some low, some left, some right, but on average, they're centered right on the bullseye. That's exactly what we want from our guess. We don't want something that's always too high or always too low. We want it to be right on target, on average.
Next up is consistency. This one's pretty intuitive. It's all about evidence. A consistent estimator is one that gets better and better the more data you feed it. So, if our guess from 100 students is pretty good, our guess from 1,000 students should be way better. A consistent guess gets closer and closer to the actual true answer as you collect more and more information.
And finally, we've got efficiency. Okay, let's go back to our archer. Let's say you have 2 archers, and they're both unbiased. Their shots are centered on the bullseye. But one archer's arrows are all over the place, while the others are in a nice, tight little cluster. Which archer is better? The one with the tight grouping, of course. That's efficiency. An efficient estimator is the one with the smallest spread, the tightest grouping. It's the most precise, sharpest guess you can possibly make with the data you have. And really, all this work, it all boils down to one incredibly powerful idea. Why do we even bother with all this? It's because if we can find a really good estimate for that one single number, that parameter, like the average height, it's like we found the secret key that unlocks an understanding of the entire population. Just stop and think about that for a second. We now have a reliable method to understand these huge, impossibly complex groups by looking at just a tiny, manageable handful. This is how we can estimate the average lifespan of a star billions of light years away. It's how we figure out if a new medicine actually works. So, if a single, well-chosen guess can tell us so much about millions, what other impossible questions can we now answer?